For over 4 decades, the semiconductor industry doubled transistor density roughly every 2 years to maintain Moore's law. But as manufacturers approached the 7-nanometer yode, they hit a hard physical wall. Classical light could no longer shrink integrated circuit features any further. In the Rayleigh criterion, the smallest printable feature is bound by the exposure wavelength, lambda. To push past the 7-nanometer limit, the industry abandoned legacy 193-nanometer DUV systems, plummeting the wavelength to exactly 13.5 nanometers. This is extreme ultraviolet, or EUV, lithography. At 13.5 nanometers, electromagnetic physics behave entirely differently. These photons carry approximately 92 electron volts of energy. This places them on the immediate border of the soft X-ray spectrum. This creates an immediate, massive engineering problem. Because these EUV photons are highly energetic, they are aggressively absorbed by virtually all forms of matter on the periodic table. If you attempt to shine 13.5 nanometer light through ambient air or transmissive glass lenses used in legacy lithography, the light is instantly absorbed and destroyed. Traditional refractive optics operate by passing light through a physical medium to bend and focus the beam. At extreme ultraviolet wavelengths, that transmission is physically impossible. The light cannot pass through any known lens. To steer an EUV beam, the entire optical exposure pathway must be stripped of air to form a high-vacuum environment. Inside that vacuum, the system must rely exclusively on catachoptic, or all-reflective mirrors, to guide the photons. The Dutch equipment manufacturer ASML is the sole corporate entity that managed to synthesize these extreme constraints into a functional, high-volume manufacturing tool. Their global monopoly is the direct result of these immutable physics constraints. The decades required to master 13.5 nanometer light created a temporal fortress, effectively locking out any competitor based on the physical time required to perfect the technology. To understand exactly how deep this business moat goes, we first have to look at the violent mechanism required to generate the light itself. The generation process begins deep within the EUV scanner's source vessel. This is a highly pressurized, kinetically hostile vacuum chamber where the photons are born. The working fuel for this system is high-purity molten tin. When tin atoms are subjected to immense thermal energy, they are stripped of multiple electrons. The resulting highly charged ionic states produce an unresolved transition array, a dense cluster of overlapping photon emissions that peaks precisely at the required 13.5 nanometer wavelength. To harvest these photons, a droplet generator extrudes microscopic spheres of liquid tin into the vacuum chamber at velocities exceeding 70 meters per second. Each droplet is roughly 25 microns in diameter, which is about 1/3 the thickness of a human hair. This generator acts as the metronome for the entire lithography tool. It operates at a strict 50 kHz frequency, firing exactly 50,000 speeding droplets every single second. As the droplets fall in a continuous stream, a specialized multi-stage carbon dioxide laser built by the German manufacturer Trumpf intercepts them. This laser system strikes each individual droplet twice. First, a low-intensity pre-pulse hits the tin. This initial strike does not vaporize the metal. Instead, the acoustic shockwave flattens the spherical droplet into a wide pancake-like disc, vastly increasing its surface area. A fraction of a microsecond later, the main pulse, delivering tens of kilowatts of pulsed optical power, blasts the expanded target, instantaneously vaporizing the metal. This extreme deposition of energy creates a localized plasma cloud that reaches temperatures of 200,000 degrees Celsius. That is nearly 40 times hotter than the visible surface of our sun. This continuous cycle of microscopic stellar explosions is currently the only known physical mechanism capable of generating enough 13.5 nanometer light to expose silicon wafers at commercial speeds. The laser-produced plasma architecture operates with a severe energy penalty. The conversion efficiency of the reaction peaks at roughly 5%, meaning only a tiny fraction of the carbon dioxide laser's optical energy is actually converted into usable extreme ultraviolet light. The remaining 95% of the input energy becomes waste heat, unwanted infrared radiation, and a highly destructive barrage of high-velocity tin-ion debris. This debris field sits just centimeters away from the primary collector mirror. Without constant mitigation, the ballistic tin particles would coat and completely destroy the delicate optical surface in less than 1 minute of operation. To protect the optics, ASML utilizes a continuous hydrogen buffer gas system. This flow of hydrogen sweeps across the mirror face, relying on both kinematic force and complex chemical reactions to repel the debris. When hydrogen radicals collide with the solid tin particles, they react to form stannane, a volatile gas. Once the tin is converted into a gaseous state, the vacuum pumps can extract it from the vessel entirely. The lithography machine is forced to continuously clean itself at the atomic level, burning through immense resources just to maintain a fraction of its original photon output. This diagram illustrates the completely catoptric, or all-reflective, optical column that takes the surviving EUV photons and guides them towards the silicon wafer. Because standard lenses absorb EUV light, Carl Zeiss SMT fabricates highly specialized Bragg reflectors. They deposit alternating nanometer-scale layers of molybdenum and silicon onto glass substrates to artificially induce constructive wave interference at 13.5 nanometers. Even with perfect atomic layering, each mirror reflects only about 70. Over a sequence of 11 distinct mirror reflections, the compounding optical loss dictates that less than 2% of the original plasma source light actually survives to reach the microchip. To prevent those few surviving photons from scattering, the surface figure accuracy of these mirrors is engineered to an unfathomable tolerance of 50 picometers root mean square. To put that in perspective, if a Zeiss mirror were scaled up to the geographic footprint of the country of Germany, the highest topological anomaly across its entire surface would be less than 1 millimeter tall. This chart shows the residual surface error by manufacturing stage. Traditional mechanical polishing techniques cannot achieve 50 picometer tolerances. To reach that baseline, Zeiss implemented a process called ion beam figuring. Looking at the final stage, IBF drives the error down to the atomic level. Inside 150-ton vacuum-isolated metrology chambers, a directed beam of neutralized argon ions mathematically sputters away individual atoms from the glass without applying physical friction. Fabricating and validating just one of these optical systems can take up to 8 months. Because of this exacting physical constraint, the fabrication schedule at Carl Zeiss dictates the ultimate limit on global semiconductor infrastructure expansion. The sheer scale of research and development required to build this optical pipeline triggered a severe financial crisis. By 2012, ASML's cash burn rate was so extreme that continuing extreme ultraviolet development threatened to bankrupt the company entirely. The major semiconductor foundries faced a prisoner's dilemma. The fixed research costs were too large for one company to bear alone, but if no one stepped up to subsidize ASML, the entire industry's transition to smaller transistors would permanently stall. This chart illustrates the capital structure of ASML's 2012 customer co-investment program. Intel acted as the anchor investor, deploying a massive €3.3 billion commitment. This forced rivals TSMC and Samsung to inject the remaining capital, fully satisfying the €5.2 billion funding target. The participating foundries secured parallel commercial agreements alongside their equity. They explicitly purchased advanced delivery priority, meaning they monopolized ASML's severely constrained manufacturing capacity and relegated any non-participating chipmakers to the back of a decade-long waiting list. By directly underwriting the research of their single-source supplier, Intel, TSMC, and Samsung eradicated ASML's financial risk, inadvertently cementing a symbiotic monopoly that controls the global supply chain to this day. This raises an obvious question. If extreme ultraviolet lithography is the most valuable manufacturing process on Earth, why can't a competitor or a heavily subsidized nation-state simply spend $1 trillion to replicate the machine today? The answer lies in a hardware equivalent of Brooks's law, which states that adding manpower to a late project only makes it later. In extreme ultraviolet lithography, injecting massive capital cannot accelerate the physical time required for atomic-level interactions. No amount of money can force a Zeiss mirror to achieve a 50 picometer flatness any faster than the strict limits of ion beam sputtering allow. The fabrication timeline is bound by thermodynamics, not budget constraints. Furthermore, building a functional scanner requires the simultaneous replication of an impossibly specialized ecosystem. A clone requires reverse engineering the multi-stage Trump drive lasers, the Zeiss picometer optics, and the intricate mechatronics required to synchronize them inside a total vacuum. ASML's moat isn't defined by patents or money. It is a trinity of multi-decade lead time, specialized capital, and uncompromising physical constraints. The Extreme Ultraviolet scanner remains the absolute choke point of global computation. It is protected by the simple fact that manipulating light at 13.5 nanometers is arguably the most difficult engineering challenge in human history.